Okay, so I want to talk a little bit about some important vocabulary and concepts that are important in pre-calculus, and they're especially important to build the bridge to calculus. And it's about functions, and it's about slopes, and it's about increasing and decreasing. And some of them are fairly straightforward and intuitive. The first one is a function is increasing if its slope is positive, and conversely, it's decreasing if its slope is negative. And a function is concave down if its slope is decreasing and concave up if its slope is increasing. And you might think those are the same things, but they're not the same things. So let's take a look at, let's picture a function like I have this one here. Okay, you can kind of look at it and you can tell where it's increasing. It's increasing, like if I'm thinking of a point, as I'm moving the point from left to right, when the point is going up, it's increasing. So it's increasing up until this point right here, which is 1.33, 0.741. And then it starts to decrease, and it decreases until it gets to 2, and then it starts to increase. And this looks like a cubic function. We can assume that it increases forever and ever towards infinity as x goes to infinity, and it goes towards negative infinity as x goes to negative infinity. Okay, so that has to do with increasing and decreasing, and that has to do with the slope. But notice there's another part on the definition that I just shared, which is when it's concave down if it's decreasing, and concave up if it's increasing. So the easy way to remember what concave down and concave up are is it's concave down if on parts where water would pour down out of it. So if you picture this as a cup and I had water in here, water would flow right down here. If you picture this part right here as a cup and you pour water in here, water would stay in it. Okay, so if it's concave up if water would stay in it, it's concave down if water would not stay in it. But the technical definition is about the slope. Is the slope increasing or is the slope decreasing? This is not the same thing as saying is the slope positive or negative, even though at the first time you see it, it's natural to think that's the same thing. What I'm saying is if the slope is positive or is it increasing, I'm actually asking how is the slope of the function changing as I move from left to right. So now I have a point here, and this point is showing the line that is tangent to the curve at any point. And what it's showing is what's the slope of the curve at any point. And this is an important concept in pre-calculus, is that functions, like in previous classes, you talk about slope, but you're just thinking of it at one point, and a lot of times it's a linear function where the slope is always the same. In pre-calculus, we start to talk about how does the slope change as we move around the function. So if you notice what's happening to this tangent line, it starts out when I'm down here, it's positive and it's very steep. It's still positive as I move here, but it's becoming less positive. And then it's becoming, when I get to the peak, the slope is 0. And then as I round the peak and start going down, it becomes negative. So if you think of moving this from left to right, I have a very positive number. I could think this is like positive 2. And then at some point, it looks like it gets to be about 1. And then it gets to be about 0. And then it gets to be about negative 1. So if I go from negative 2 to 1 to 0, or sorry, if I go from 2 to 1 to 0 to negative 1, that's decreasing. Okay, so concave down is when the slope is decreasing. It's when the tangent line is rotating clockwise. But you notice at some point it stops rotating that direction and it starts rotating the other direction. And now that's when the slope is increasing, because here I have a negative slope. Down here I have a 0 slope. And as I move up here, it's positive and it gets even more positive. So this is the slope increasing, and this is where the function is concave up. So I would say the point where it changes, which has a name, but I don't want to give you the name yet, is right in between these two, the minimum and the maximum. So whatever the point is between 4/3 and 6/3, I guess that would be 5/3. So if I put in a point 5/3, comma, f of 5/3, that point right there is the point exactly when the concavity changes from concave down to concave up. I want to say one more time, it's concave down and now it's concave up. Okay, so more definitions. It has a minimum or a maximum value at any point where its slope changes. If the slope changes from positive to negative, it has, you can think of this in your head, what would it have if it changes from positive to negative? Well, let's think of this point now. As the slope is going from positive to negative, what does it have? It goes from positive to negative. That looks like a maximum. If the slope changes from negative to positive, it has a minimum. And now, one other thing is all minimums and maximums are local. Okay, I would call those I would say in this case, the function has a local maximum at x is equal to 1.33, y is equal to 0.741. I would say it has a local minimum at x is equal to 2, y is equal to 0. But they're only global if they are the highest or the lowest over the entire domain. Okay, so in this case, in this function, there is no global minimum, there is no global maximum, because while this may be like if you were hiking along this path, you may get to a peak and you may eat your sandwich and then you may start to descend. But then if you kept hiking, you would start to ascend and you would get to higher points than this 1.33. And there would be no point at which you could say there's no way up, because you could always go further up if you go to the right. And similarly, if you're going to the left, there'd be no point where you could say there's no more down, because it just keeps going down forever and ever. So this function has a local maximum, it has a local minimum, but it does not have a global minimum or a global maximum. If we look at this function right here to kind of tie everything together, I might say over what intervals is it increasing? And it looks like it's increasing over this stretch, and it looks like it's increasing over this stretch. So if I want to write those in some succinct kind of way, I would say -4, this is interval notation, it's going from -4 to 2, and I'm going to put parentheses because at the points of minimum or maximum, it's not really increasing or decreasing. Put a little U, that means union, that means and. Also, 6 to infinity. It's decreasing from here, like on this stretch right here, and it's decreasing on this stretch right here. So it's decreasing from, what's this, negative infinity to -4, and from 2 to 6. It's concave up. Okay, so where it's concave up is where slope is positive, and it's where I'm going to have to leave this yellow line in there. It's concave up where the slope, where it's the slope is increasing. So here you can see that I have my slope is negative. It's starting to get less negative. It becomes 0, and it starts to become positive. And then at some point, it changes, and it's positive, but now it's starting to become less positive. Now it becomes 0, and now it becomes negative. And then it's becoming less negative, and it becomes 0, and then it becomes positive. Okay, so it's concave up in between negative infinity till this point. So it's going to be negative infinity to, and that point is actually going to be whatever is right in between these two, the minimum and the maximum. So right in the number that's in between -4 and 2 is -1. And it's also concave up from whatever point is between 2 and 6, which is 4 to infinity. And it's concave down in the rest from -1 to 4. Where does it have a local minimum? Well, it has a local minimum at -4. And I'm going to put both the x and the y values, okay? And if you said, what is the local minimum? You might say that the local, well, this isn't a good example because the coordinate is -4 comma -4. And 6 comma -2. So what I was trying to say is, if I think about this point right here, and I think about how could I word the question and how could the answers be a little bit different? If I said, where is the local minimum? You could say, where is it? It's at x is equal to 6. If I say, what is the local minimum? Technically, what is the local minimum is like, what is the lowest point on the path, which would be -2, okay? I don't think I'll be tricking you in this class with that kind of wording of the question, but I think it's important to pay attention to that. The idea of where would I find that the bottom of the path? That would be when x is equal to 6. What is the bottom of the path? That would be when y is equal to -2. What is the global minimum? Is there a global minimum? There is a global minimum because the function goes towards infinity on both sides. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to positive infinity. So the global minimum is going to be at -4 comma -4. A local max is going to be at 2 comma 4. And does it have a global max? It does not have a global max because it ascends on both sides. And so the final word or term or definition is a point of inflection. And a point of inflection is where concavity changes. And in this case, I have 2 of them. And I don't know exactly what the y coordinate is, but I'm going to say that it's somewhere at -1 comma, well, let's say -1 comma 0. That's where it changes from concave up to concave down. And then it looks like at about 4 comma 1, it changes from concave down to concave up. And so a good activity to do, to think about, to try to put some of these ideas together that's not exactly intuitive would be to sketch a curve that's increasing and concave down, one that's increasing and concave up, one that's decreasing and concave down, and one that's decreasing and concave up. And so I have to think about these and what's it going to look like. If I sketch one that's increasing and concave up, then it's going to look kind of like a quadratic. And what would it look like if it was increasing but not concave up, increasing but concave down? Well, it would be getting flatter, and it'd be kind of like a root function. What would it look like if it's decreasing in concave down or decreasing in concave up? Well, I think decreasing in concave up would look like that, where it starts really negative and it's getting flatter. And what would decreasing and concave down look like? It would start real flat, and then it starts to get real steep. That's the end of the lesson.